Let's do problem 15. So we have this right regular hexagonal prism. So we'd like to cut this prism by cross section passing through KJ and AB. And the question is to find the area of this cross section. All right, let me try to sketch this cross section. So pass through AB and the KJ. So it passes through some middle point on IC. It also passes through a middle point on LF. So let me call this point M, this point N. So our goal is to find this area. Okay. Now let me draw this section. It's also a hexagon, but not regular. M, N, A, B. So this cross section is symmetric. We can divide by connecting MN. We can divide this into two congruent trapezoid. So we know AB is 3 and the KJ is also 3, right? That's just the side lines of the base. So they are both 3. And MN, okay, MN equals FC. Let me draw a regular hexagon here. So FC is twice AB because I can connect this diagonals. It divides the hexagon into six identical equilateral triangles. So AB is 3, so FC must be 6. And FC is equal to MN, okay? Because both MN are middle point of this IC and the LF. So MN is also 6. So our goal is to find this height, okay? JB. Now, let's try to calculate this JB. So I'm going to connect JB in this prism. And I consider also JD and the BD. This becomes a right triangle. So we can solve this right triangle. This is J, D, this is B. So first we know that BD is 3 root 3. Okay, 3 root 3. And then we have JD equals 13. That's the height of the prism. And we must have JD perpendicular to BD because this prism is a right prism. So the JD is perpendicular to the plane, to the base. So of course it's perpendicular to BD. So this is a right triangle. Now let's solve this, the hypotenuse. JB is JD square plus BD square, and then we take square root. 13 square plus 3 root 3 square. Okay, and this becomes 169 plus 27 root. This is 196, which is 14. So JB is 14. And of course, it's divided into 2 sevens by MN. So 7. Now we can find the area of area of this cross section. AB MJ KN is twice the area of MJ KN, which is 1/2. Okay, twice. The area of the trapezoid is KJ plus MN times 7 divided by 2. Okay, and then we can cancel these 2's. So the answer is just kj plus ma. So it's 3 plus 6 times 7, which is 63. The answer is 63. All right, let's do problem 16. We have this quadratic equation with the coefficient a, b, c, positive integers. So what's the smallest possible value of a such that this equation has two distinct positive roots between 0 and 1? So let me try to draw this graph of this quadratic function. So let me do the function y equals a x squared minus bx plus c. So the roots of the quadratic equation corresponds to the intersection of the curve with the x-axis, right? Let me sketch the picture. 0, this is a 1. So the picture has to be something like the following. Okay, this is a y equals ax squared minus bx plus c. Okay, and we know the axis of symmetry is between 0 and 1. This line is x equals b over 2a. Okay. Now let's try to see what kind of algebraic condition should be satisfied to guarantee everything in the problem. All right, first we know that the axis of the symmetry must be between 0 and 1. b over 2a is larger than 0. It's less than 1. Of course, it's larger than 0 because both are positive integers, but it's less than 1. That's something we should be careful. Okay. And next, we see that when x equals 1, the y should be positive. Okay. So when x equals 1, the value of this function is positive. So a minus b plus c should be positive. And finally, we know that we have two distinct roots. So we have this discriminant, b squared minus 4ac. This must be positive. All right, we need these three conditions to guarantee everything. And of course, on the other hand, everything in the problem is characterized by these three conditions. All right, let's see how to find the least possible value of a. First, we know that from here, we can rewrite these equations as follows. So this three condition is equivalent to the following. So b is less than 2a, the first condition, right? And the second condition is a plus c is larger than b. The third condition is b squared should be larger than 4ac. And all of them are positive integers. Now let's discuss the values of a, b, c. So first we have some inequality as follows. We know that 4a squared equals 2a squared. And 2a is larger than b, so 2a squared is larger than b squared. And b squared is larger than 4ac. 4ac. From here, we can cancel one c. Oh, sorry, we can cancel one a. This implies a is larger than c. Okay, a is larger than c. So c is at least 1, so a is at least 2. All right, then we can find some condition for b. b squared is larger than 4ac. Because a is at least 2, c is at least 1. This is 8. So b squared is larger than 8. That means b squared is at least 9 because b is integer. Then b is larger or equal to 3. Okay, let's discuss the value of b and see if there exists some a and c satisfy everything. Now let's discuss the case if b equals 3. If b equals 3, we have a plus c larger than b. Okay, so a plus c larger than 3. If a plus b larger than 3, we will see that a plus c is larger or equal to 4, right? And then a is larger than c. So a has to be larger than 2. If a is 2, c has to be 2. So a is larger than c. So a is larger or equal to 3. Okay. And then we see that this is impossible because on the other hand, we have on one hand b squared is equals 9, but on the other hand, we see that 4ac, because a is at least 3, so this is at least 12. So b squared cannot be larger than 4ac. This is invalid. So b cannot be 3. So now let's say b equals 4. If b equals 4, we have that a plus c is larger than 4, and b squared is 16, larger than 4ac. Okay? So that means ac is less than, a times c is less than 4. A plus c is larger than 4, so it's at least 3. But a times c is less than 4, so there's no solution. Okay, from here, from a plus c larger than 4, we see that a is larger or equal to 3. But from here, we have that if a cannot be 4. Okay, but if a is 3, that means c must be 1. But in this case, a plus c is just 4. It's not larger than 4. So this is invalid. Okay. All right, finally, let's do b equals 5. Let me do it on this side. So the third case, b equals 5. b equals 5, we similarly, we have a plus c larger than b, so larger than 5, so it's larger or equal to 6. And on the other hand, b squared is larger than 4ac, b squared is 25, larger than 4ac. That implies ac is less equal to 6. Okay, ac is less equal to 6. But we know that a plus c is larger than 5. We see that a plus c is larger or equal to 6. That means a is larger or equal to 4. It's larger or equal to 4. So if a equals 4, we see that c is larger or equal to 2 because the sign is larger or equal to 6. But this doesn't work because in this case, a times c is larger than 8. Okay, larger or equal to 8. That's larger than 6. But we have a times c less equal to 6. So this is invalid. Now let's see a equals 5. If a equals 5, we can choose c equals 1 to satisfy both. Okay, both means a plus c is larger than 5 and a times c less than 6. So this works. So a equals 5, b equals 5, c equals 1. So this kind of values satisfy all conditions. So the smallest value of a is 5. The answer is 5. All right, let's move to problem 17. So we have this following equation for trig functions. We'd like to find m over n. Okay, m plus n. Okay. Then, all right, let me record the law of sine. So I'd like to, based on the numbers, these angles in the problem, let me draw the following triangle. I have the following angles. This is A, B, C. Angle C is 60 degrees. Angle A is 35. Because 35 is from the equation. Angle B is 85. Right? Now we have law of sine. Law of sine says that Okay, if I set this side length A, B, C, A divided by sine A equals B divided by sine B equals C divided by sine C. Okay, so this is law of sine. So in particular, maybe we need to shrink this triangle or enlarge the triangle a little bit so that this this quotient just equals 1. Okay, we can rescale this triangle. Let's just take A equals sine 35, B equals sine 85 degree, C equals sine 60 degree. Okay, so we have this triangle. Next, we record the law of cosine. The law of cosine says that we have a squared plus b squared minus twice ab cosine c. Okay, here cosine c is just cosine 60 degree equals c squared. This is law of cosine. Right? And then let's plug in this values of a, b, c. A squared is sine 85 squared, and the b squared is sine. Okay, sorry. A squared is sine 35. B squared is sine 85 squared, and then minus. Okay, cosine 60 degree is just 1/2. So this 2 and 1/2 cancels. Basically, we just have A times B. A is sine 35, B is sine 85 equals C squared. And C is sine 60. 60 is root 3 over 2. The square is 3 over 4. Now let's compare this equation with the equation given in our problem. They are essentially the same. Because first we have sine 35 equals sine 35, sine 85 equals sine 85. And then in the problem, we have cosine, right? So basically cosine can be replaced by sine. So cosine 5 equals sine 85 because they are complementary. And also for sine 35, that's cosine 55. Okay. So these two equations are equivalent. So that means Mn is basically C squared. It's 3 over 4. So M equals 3, N equals 4. M plus N is equal to 7. So the answer is 7. Now let's do problem 18. So we have a complex number problem here. All right, this equation z to n plus 1 minus z to the nth power minus 1 equals 0. So let me rewrite this a little bit. This equals z n plus 1 minus z n equals 1. So I can factor the left-hand side part. This is z n, z minus 1 equals 1. So here we know that this equation has a complex root whose modulus is 1. So we can add this modular, the absolute value or the modular. So we have was 1. So this is equivalent to modulo z n z minus 1 equals 1. We already have the first part equals 1. So this implies z minus 1, the modulus is also 1. Okay, from this information, we can basically solve z. So let me draw this picture. So modulus of z equals 1, that means it's on the unit circle. So let me draw a unit circle. So this z must lie on this circle. 1, what is 1? What is 1? 1. On the other hand, z minus 1 modulus 1. So that means if we draw a unit circle with center at 1, so the z is also on the blue circle, but we know there are only 2 intersections. So z must be one of these values. Okay. So there are 2 choices for z. All right, now let's discuss the value of z. First, okay, we have that. Because here we are dealing with this z to certain power. It's convenient to express z in terms of the exponential. So for the first one, we know the angle is like 60 degree, right? This is 60 degree. This is also 60 degree. So or just pi over 3. Pi over 3. This is pi over 3. All right, now we see that z has 2 choices. z1 is exponential pi over 3 I. This is the first choice. Or, so this just corresponds to 1/2. Okay, cosine, let me write more details. Cosine pi over 3 plus I sine pi over 3, which is 1/2 plus root 3 over 2I. This is one choice. Or z equals exponential, because this is to the negative direction. So it's basically negative pi over 3 I. So this is cosine negative pi over 3 negative pi over 3. Okay, this is 1/2 minus root 3 over 2I. Okay. All right, let's discuss these 2 cases. If z equals exponential pi over 3I, now we have, let's plug in into the equation, okay? So first, let me express z minus 1. So z minus 1 is minus 1/2 plus root 3 over 2I. So here we have z minus 1 is basically here. This is z minus 1. Okay? So this corresponds to the angle 120, which is 2 pi over 3. Exponential 2 pi over 3I. Right, now let's come to z and z minus 1. This becomes exponential pi over 3I to the nth power times exponential 2 pi over 3I. This can be combined as n pi over 3 plus 2 pi over 3I. And we know this has to be equal to 1. So it equals 1. That means it equals exponential 2k pi I. K is an integer. So we have n plus 2 pi over 3 equals 2k pi. K is an integer. That means n equals 6k minus 2. So n has to be 6k minus 2. Right, now we have that n is between, n is from 1 to 100. K can be 1 to 17, up to 17. Okay? If k is 17, n is just 100. So we have 17 choices. But now we still need to discuss the other case. Z equals, if Z equals exponential minus pi over 3i, then Z minus 1 equals minus 1/2 minus root 3 over 2i. So this corresponds to a different point. Let me draw here. This corresponds to a point here. And this angle corresponds to negative 2 pi over 3. Or 4 pi over 3. Let me write 4 pi over, exponential. Because this is a 4 pi over 3, okay? Then we plug in this into the equation. Zn, Z minus 1 equals exponential negative pi over 3i exponential 4 pi over 3i. This can be simplified into exponential 4 minus n divided by 3 pi I. And this equals 1, okay? But 1 we know equals exponential 2k pi I. So we must have the following condition for n. 4 minus n must be equal to 4 minus n divided by 3 is 2k pi, so 2k, which means n is minus 6k plus 4. Okay, n is minus 6 plus 4. And then let's review this a little bit. This is equivalent to 6 for different k plus minus 2. So I'm considering the remainder was divided by 6. So the remainder is 4. This is equivalent to the previous case. So these two are basically equivalent when just consider the remainder was divided by 6. So if you count this n, they will be the same as the previous solutions. So we still have the same solution. So same to the above case. So we don't have more n's. So the answer is just 17. Okay, that's the solution. All right, problem 19. We have this indefinite equation for a and b. A is a prime number, and b is a positive integer. So both are positive integer. We have the following equation. What's the sum of the digits of a? So basically, we need to solve for the value of a. All right. So let's look closer to these numbers. We notice that 509 is a prime number. All right, this is good because 9 and 5, okay, GCD of 9 and 509 is 1. So let's use some divisibility test or properties to find some property of A and B. For example, we know this equation is a multiple of 509. So 509 must divide 9 times 2a plus b. And because 509 has GCD equals 1, so that means 509 divides, square, 2a plus b square. And that means 509 divides 2a plus b. So 2a plus b must be a multiple of 509. So let's denote the following. 2a plus b equals 509 times k for some integer k, okay? Then we have 9 times 500, okay. So if I put 9 into the square, it's basically 3 times 509k square. This is basically the left hand side. This equal to 509 times 4a plus 511b. On the left hand side, we have 509 squared. On the right hand side, we just have 509. So there must be another 509. So we have that 509 also divides 4a plus 511b. Okay, so let's denote and it's also square. Okay, it's also square. So we must have 4a plus 511b to be 509 times some square. Okay, because the whole number is square. So let me denote by t square. Okay. All right. Now we can relate k and t. So basically we have 3 times 509 k. This is the left hand side equals 509 t squared. So that means t is 3k. T is 3k. So there's a relation between t and k. All right. Let's try to find more properties of a and b. Okay, we have 2a plus b equals 509k, and 4a plus 511b equals 509 times 3k squared. So it's 9k squared. Let me call this equation 1, this equation 2. Okay, so let's do the following. The second equation minus twice the first equation. So we can cancel a. And the 511 minus 2 is exactly 509. So we got the following. Left hand side is 509 b. The right hand side is 509 times 9k squared minus twice 509 k. So from here we can cancel 509 to solve b equals 9k squared minus 2k, which is k times 9k minus 2. So this is the expression of b in terms of k. And next we can express 2a. 2a is 509k minus b. We can plug in and solve it. We got 511k minus 9k squared. So this is k times 511 minus 9k. Okay, this is good because we know that a is a prime number. So and here we write 2a in terms of a product. So k cannot have a lot of choices. So remember that a is prime. So basically we will have that k equals 1 or 2. That's only 2 choices. Now let me give you more explanations. I will explain why. So first, let's say k equals 1. K equals 1, we get a solution basically. 2a equals 1 times 511 minus 9. This is equal to 502, which means a is 251. And the b, we can solve b. B is k times 9k minus 2, which is 7. So a is 251, b is 7. And that works. This is a solution. And then let's discuss k equals 2. If k equals 2, we have 2a equals 2 times 511 minus 18, which implies a equals 511 minus 18, which is 493. But the 493 is not a prime number because we can factor this into 17 and the 29. So this is invalid. And next, let me explain to you why k cannot be larger or equal to 3. First, we know that 511, the remainder was divided by 9 is 7. Okay. So next, let me show you that if k is larger or equal to 3, a cannot be a prime number. If k larger or equal to 3, if k is even, two cases, right? K even. If k is even, we have a equals k divided by 2. K divided by 2 is the integer times 511 minus 9k. This because k is larger or equal to 3, so it's at least 4. So k divided by 2 is a number larger or equal to 2. And the 511 minus 9k is also a number larger or equal to 2. So that means a is not prime. So next, if k is odd, a equals k times 511 minus 9k divided by 2. Because k is odd, so 511 minus 9k is even. So this divided by 2 is another integer. And 511 minus 9k is at least 7. A divided by 2 is larger than 2. So this is an expression of a in terms of two products. Each one is, neither is 1. So it's not prime. So we must have a solution in the first case, k equals 1. This is our solution. And a is 251. The sum of the digits is just 2 plus 5 plus 1, which is 8. So the solution is 8. All right, let's do problem 20, the last problem. So we have this tetrahedron with 6 faces, congruent triangles. And we know the side lines AB equals 2. Let me use black. AB equals 2, BC equals 3, and AC equals 4. AC equals 4. So 6 faces, 6 triangles are congruent to triangle ABC. So this triangle will have side lines 2, 3, 4. So 6 triangles are always have, all of them have side lines 2, 3, 4. And that means, okay, we can decide other sides. So that means AD has to be 3. If AD equals 2 or 4, then we will have an isosceles triangle, which is not allowed. So AD has to be 3. And then CD must be 2, and the BD must be 4. Okay, so we see that for this tetrahedron, the opposite edges have the same length. So this kind of a tetrahedron we call isosceles tetrahedron. All right, let's discuss the coloring. We have 3 colors to choose. Each color must be used twice. So we just discussed the, how many pairs of the opposite edges are colored the same. Okay, so first, let's discuss the case 1. Okay, let me mark here. We have 3 pairs of edges, of equal edges. But these different pairs have different side edge lengths. So first, let's discuss that each pair of edges are colored the same. So we'll have 3 pairs of same colored edges. All right, this is very easy because we have 3 colors and we have 3 pairs. Basically, we just do 3 factorial. Because for the first pair, we have 3 choices. For the second pair, we have 2 choices. For the last pair, there's 1 choice. So we have 6 ways to color the tetrahedron in this way. Next, so we have fewer pairs of edges with the same color. All right, notice that we cannot have 2 pairs of edges have the same color. If 2 pairs of edges have the same color, the third pair must be the same, must also be colored the same. So we have 3 pairs. So that's discussed already. So next we need to discuss, we have only 1 pair. 1 pair of edges with the same color. Okay. So for example, let's first decide this pair. So we have 3 choices. And next, we decided which color to be colored to here. So we have 3 choices. So basically, we have 9 choices. And then let's discuss if this pair's colors are determined, how many ways can we color the rest edges? So for example, let me take example. We take like AC and BD are the chosen pairs. And we suppose the color is blue, just like the picture shows. And then we discuss how to color the other 4 edges. So let me just draw this picture. So A, so here A, B, C, D. Okay, A, B, C, D. And A, B is 2, 3, 3, 2, okay? All right, let's see how to color these 4 edges. So we know that we already used blue colors. What remained was 2 yellows and 2 reds. So we have 2 yellows and 2 reds. But we cannot have opposite edges with the same color. So we have the following way to color it. AB equals R, AD equals Y, and the CD equals Y, BC equals R. Okay, and basically that's all. If you change the order, because we are allowed to flip, to rotate, so it will always be the same. Okay? So for example, if you rotate a little bit, because same color cannot be opposite, so they must be adjacent. So the other choice may be this, R, Y, Y, R, but these 2 are equivalent because we can flip the tetrahedron and they are equivalent. So basically we only have 1 choice once we fix this pair and the color. So there will be 9 ways to color the tetrahedron in this way. So we still have one case to discuss. This case is that we have, okay, for each pair of edges, they have different color. So each pair of edges have different color. That means we don't have any pair of edges with the same color, okay? All right, we should discuss each pair. Now let's first color. Let's choose one pair and color this first. First color the pair. Say ACBD, for example. And they have two different colors, right? And now let me try to find a way such that we don't allow rotate, or we can avoid flipping. So basically we can do the following. I can make an ordering between the colors. Between these colors, for example, B is larger than R, is larger than Y. Let me just make an order for the colors. If this is done, and we can basically make, we require the color of AC. AC is larger than the color of BD. Okay, why? Because if the color of AC is smaller than the color of BD, I can basically flip. So the upper one is larger color. So now if I assume this ordering and I put this requirement, basically I just put this heterogeneity and don't flip. Okay, let's just don't flip. All right, so here in this way, we can color AC and BD in three ways, because we just need to choose two colors. We have three colors, we choose two colors, and the order is automatically determined. We have three ways to color AC and BD. Next, let's consider the other four edges. So it's A, B, C, D. Let me do it here. Okay. So for example, let me choose this two color to be blue and R, for example, right? Blue and R for AC and BD. So basically AC is blue and BD is R. And what remain, we can use B, let me use B and R. B, R, and the two yellow to color the other four edges, right? Let's see how many ways can we color it. So this two yellow color must be adjacent. Otherwise, we have a pair of the same color, so they must be adjacent. So it turns out that we have four ways to color it. So AB is 2, 3, 3, 2. So let's see this. So there are two ways to put this yellow color. For example, I can color AB and color AB and AD to be yellow. Because or I can color AD and DC to be yellow. Okay. Yeah. Because we cannot flip, so these are all different. These are all different, and there's no more other coloring for this yellow, because we can rotate. We can rotate on the plane, but we cannot flip. We are not allowed to flip because we determine this ordering of this color. Right. Next, we consider the coloring of the blue and R. So the blue and R, okay, for each kind of coloring, yellow coloring, we have two ways to color blue and R. Because on the left, right, left, we have two ways to color. For example, this is blue. This is red, or this is red, and this is blue. Okay, they are different because we cannot flip anymore. All right, next for this color, we have same, right? Same idea. Suppose this is blue, and this is yellow. This is red. And also maybe this is a blue, and this is a red. So we have four ways to color this edges. So totally we have 3 times 4, which is 12. So there are 12 ways to color the edges. That there's no pair of same color edges. All right, let's sum up all the cases. So the solution will be the sum of these numbers. So answer is 6 plus 9 plus 12, which is 27. So the answer is 27. All right, that's the end of this video. Thank you for watching.